Hi, my name is Itamar Oliveira. I am a graduate student at Cornell University, working with Camil Muscalu, and I'm going to talk about some of the results of my dissertation on the Fourier extension problem for the paraboloid. This is joint work with Camil. Okay, so let's start by defining what the Fourier extension operator is. If you take a function from 0, 1 to the power d, complex valued, defined on a compact piece of the paraboloid y equals x squared, then we define its Fourier extension to be the integral of g against this linear phase here, e to the minus 2 pi I x dot xi times this quadratic modulation, e to the minus 2 pi I t x squared. This looks a lot like the Fourier transform. It turns a d-dimensional function g into a d plus 1 dimensional function edg psi and t. So psi and t are free parameters in this integral. And this is what we call the Fourier extension of g to the paraboloid, to this compact piece of the paraboloid. Okay, so about this operator, we have a very famous conjecture by Stein in the late 60s, early 70s. The conjecture says the following: if the pair 1 over p, 1 over q is in the set that I'm calling green union red, then this operator that we just defined should map LP to LQ, LQ in RD here. And the green union red is this region here that I plotted. Instead of describing analytically what it is, I prefer to plot the picture. It's this trapezoid here. And the reason why I divided it into pieces is because when P is 2, everything that is below this point here in the green region, for every pair 1 over P, 1 over Q, in this green region, this conjecture is known to be true as a consequence of the Thomas Stein or Stricker's theorem. And depending on the dimension, there's a little bit that is known in this red range here. But in general, it's open, except for some results that I'm going to mention in a few minutes. And by some interpolation results, it's known that it's enough to prove that this conjecture holds for points that are closer and closer to this corner here that is a critical point. It's the most important point of the whole range. Okay. So the effort over the last 2 decades has been focused on proving estimates for pairs 1 over P, 1 over Q in this red region, closer and closer to the critical point. And among the techniques that have been used over the decades, we have insights from geometric measure theory, combinatorics, topology, number theory, and more recently polynomial partitioning. This is the approach that has given the best results as of today. And we have works from many people: Tao, Bourgain, Vargas, Wolf, Vega, more recently Larry Guth, and the school that is used in polynomial partitioning. Okay, so the conjecture has been fully solved only in dimension 1 by Pfefferman and Zygmunt, late 60s, early 70s. And some of the best bounds up to this day are the following. Wang proved that E2, so the two-dimensional, on the two-dimensional paraboloid, she proved that E2 should map L3 to L3.2307 and so on, where the conjecture says that it should map L3 to L3 plus epsilon for every positive epsilon. And in higher dimensions, the best bounds are due to Larry Guth, Jonathan Hickman, Keith Rogers, and Joshua Zhao. There's a long list of bounds. It depends on the dimension, but collectively they have the best bounds. And one of the main ideas behind the current approaches is to linearize the contribution of the quadratic phase in the integral that I defined above. So if this is the extension operator, what one usually does is you can decompose this integral by means of a wave packet decomposition at an appropriate scale, and then you try to exploit the cancellation between these wave packets. This is very roughly speaking. Of course, I'm skipping a lot of details here, but this is the idea. You linearize the quadratic modulation and you try to turn this problem into skewed Fourier coefficients, say into Fourier expansions in different directions at an appropriate scale. And then the challenge becomes to estimate the contribution, the interference of these wave packets, constructive or destructive. So in our work, we maintain the quadratic phase intact. We don't linearize it. And the goal for the rest of the talk is to give an overview of a broader framework that unifies the treatment of both linear and multilinear variants of the Fourier extension problem. Okay, so let's keep things simple and take d equals 2, just to simplify the arguments. So this is the theorem in dimension 2. If G splits, if you can write G as a G1 of x times G2 of y, then the extension operator applied to this kind of function, to tensors, maps L3 to L3 plus epsilon for every epsilon bigger than 0. The sketch of the proof that I'm about to show is not the simplest way that we know how to prove this. Recently, we talked to Jonathan Bennett, and we learned that the argument that we have can be done in a global way. And this works well for the linear extension problem, but we haven't found a way to generalize this global interpolation that he suggested in the multilinear case. And I'm going to talk about that a little bit later. Okay, so the key tools are the same result in dimension 1 and the Pythagorean theorem that is translated in this setting as Bessel's inequality. So I'm going to give a very rough sketch of the proof here because I still want to talk about the multilinear problems. So the first idea is that it's enough to prove the same bound for a discretized model. So by abuse of notation, I'm going to denote by E2 this model here. E2G is now the sum over integers, triples of integers in Z3 of this scalar product here between G and this bump that is modulated twice linearly by a vector in ZD n and quadratically by m, that is an integer, times a bump that is just the indicator function of the cube n plus 1, m n plus 1. All right, so this is a step function. Basically, on each such square, its value is this number. And through a discretization process, it's enough to show that if this operator here maps L3 to L3 plus epsilon, then the original extension operator does the same. Okay, and the way we deal with this operator is by running a stopping time with the scalar quantities G, phi, and m. So we basically select triples of integers for which this quantity here has about the same size. And then we explore the 1D result and the Bessel at a local level. Okay, so the first step is to dualize this operator, which means integrate against a function h on both sides, and use the fact that if G is a tensor, then this 2D scalar product here splits as the product of two 1D scalar products. This is because this function phi, that is a bump modulated twice, already has a tensor structure. So if G has a tensor structure, you can effectively split this 2D integral here into 1D integrals, and you end up with this product here of two 1D scalar products times this product of the 2D scalar product that comes from the dualizing function h. So now the job is to bound this trilinear form and use a restricted weak type interpolation argument to obtain the bound that you want for it, so that the original operator satisfies the property that you want. Okay, so the setup of a proof involving restricted weak type interpolation is you fix U1 and U2, measurable sets in 0, 1, F, a measurable set in R2, and these sets are so that their indicator functions bound the input functions of the trilinear form. So indicator function of U1 is bigger than the absolute value of G1, and so on for the other two functions as well. So the first step is to split Z3 into sets where each one of these scalar products that appears here has controlled size. So we define AL1 to be the set of pairs in Z2 for which this first scalar product here, G1, phi, N1M, has size about 2 to the minus L1. AL2 will be the set of pairs in Z2 for which the second scalar product that appears here has size about 2 to the minus L2. And to deal with the third scalar product, we define AL3 to be the set of triples in Z3, for which that quantity has size about 2 to the minus L3. Now we define a final stopping time set that encodes the information from each one of these sets. This is what we call the X, L1, L2, L3. That is the set of triples in Z3, for which N1 and 2 and M, for which N1 and M is in AL1, N2 and M is in AL2, and the full triple is in AL3, where ALs are the sets that we just defined. So if you compartmentalize things in this way, you can bound the original trilinear form like this. You can say that the absolute value of this trilinear form is bounded by the product of these three sizes times how many elements you have on each set of indices, right? This is by the definition of the set X. And now the job is to bound this cardinality here in different ways so that you can make the series converge and you get precisely the estimate that you want in the end. We estimate this cardinality in three different ways, exploring orthogonality, 1D theory, and disjointness of the supports of these cubes. I will skip the details of these estimates. I'm just going to tell you which estimates we have. We have one estimate involving the measure of f, where f is the function, is the measurable set whose indicator function bounds h, the dualizing function. And we have two more estimates involving E1 and E2, where E1 and E2 are the measurable sets whose indicator functions bound the absolute value of G1 and G2, the input functions of the extension operator. So with these three estimates, if we interpolate among them with appropriate weights, then we can show that the trilinear form that we had before is bounded by this product of measures. And the same argument that I showed holds for exponents that are arbitrarily close to a third, and 2/3 here. So you can use multilinear restricted Wick type interpolation theory to show that this bound implies that the original operator, each restricted to tensors, maps L3 cross L3 cross L3 to L3 plus epsilon. The same kind of estimate holds in higher dimensions. It's the argument is very similar. And again, this is not the easiest way that we know how to prove this theorem for tensors, but it's a good proof of concept for how the proof goes in the multilinear story, for which the same kind of simpler argument does not hold. At least we haven't found a way to adapt it. Okay, so let's talk about the multilinear theory a little bit. I'd say that the key word in this theory is transversality. So let's see what this means. If k is between 2 and d plus 1, then we say that a k tuple S1, S2, all the way to Sk of smooth codimension 1 submanifolds is C transversal if the volume of the solid that you get by picking one normal vector to each cap is bounded below by C, no matter which unit normal vector you choose on each cap. So here I plotted a picture of what the three transversal caps would look on the paraboloid. And just a remark for the notation that I'm going to be using from now on. We define the extension operator on top of the interval on the cube 0, 1 to the power d, but you can define it for general domains. So in particular, when I write ESJ, I'm talking about the extension operator with respect to the cap Sj, that is the graph of the domain Uj on Rd. Okay. All right, so this is the extension operator associated to a particular cap Sj. So the k-linear extension conjecture says that if S1, S2, all the way to Sk are transversal caps on the d-dimensional paraboloid, then the product of k-linear extensions, each extension to one of these submanifolds, in this case a submanifold of the paraboloid, the cap of the paraboloid, this product here is in LP if the input functions are in L2 for every p bigger than or equal to this threshold here. Okay, so let's see what has been done so far about this. When k is 2, this has been fully solved by tau up to the endpoint, and the endpoint has been recently solved by Lee. When k is d plus 1, we know this as the BCT theorem, Bennett-Carberry-Tau theorem, solved up to the endpoint as well. And k equals d was recently solved up to the endpoint by Bijanatu. Under to the best of my knowledge, this is all that has been done so far. So under the assumption that one of the functions involved in this problem, one of the GJs has a tensor structure, we obtain that the conjecture above holds with a weaker transversality hypothesis. So let me quickly define what this means. When k equals 3 and d equals 2, this weaker transversality hypothesis is the following. We say that 3 cubes in R2 are weakly transversal if for every j between 1 and 3, so for every such cube, you can find a permutation of the other two. So L1 and L2, a permutation of 1 to 3 minus j, such that the projections of the qj with respect to the other two cubes are disjoint. So in this particular case, these 3 cubes here are weakly transversal because for q1, this first projection here, the interval 0, 1, is disjoint from 0, 2. And this projection here on the y-axis is disjoint from 4, 5, that is the projection of q3. So these 3 cubes are weakly transversal, but they are not transversal because the line y equals x crosses the 3 of them, and one can check from the definition of transversality that this violates the transversality condition. All right. This definition was motivated by the 1D bilinear theory and by the way we exploit transversality in the 1D bilinear case. And the theorem that I'm going to state holds for caps that are that have this configuration here, that are just weakly transversal, that are not necessarily transversal, when one of the functions has a tensor structure. So we gain a little bit because we weaken the hypothesis, but we lose in the end the conclusion because, of course, we can prove this in general because it's known to be false when the 3 functions are generic. Okay, this picture here is what the 3 transversal cubes would look like in this case. So there can't be a line that intersects the 3 of them at the same time. And we call this weakly transversal because one can show that every transversal set of cubes can be decomposed in a way into weakly transversal sets of cubes. Okay, so under weak transversality, this is what we can prove. So for k weakly transversal caps on PD, then the conjecture that I stated above holds for P strictly bigger than the threshold that the conjecture predicts if one of the GJs has a tensor structure. It doesn't have to be a full tensor. You don't have to split it into all the variables, but it should have blocks of functions. I'm omitting this just to keep the discussion as simple as possible. And as I mentioned before, this is false in general without the tensor assumption. This in particular recovers the k-linear conjecture with the extra hypothesis that one of the functions is a tensor. Because since as I mentioned before, if you are given a transversal set of cubes, you can decompose the set of cubes into weakly transversal sets of cubes. Okay, so there are 2 building blocks in the proof of the theorem above. It's in the same framework as the linear theorem that I started the talk with. The first building block is the bilinear extension for the parabola. That is what motivated the definition of weakly transversality. So let me define the model that we use for bilinear extension. It's very similar to the model of linear extension, but now we have 2 scalar products here in the summand. G1, phi 1, and m. So this is the first input function integrated against a bimodulated bump. And the second input function integrated against another modulated bump with the same modulations here. The difference between these 2 bumps that I am represented with these indices is the support of the bumps. So these are 2 1D scalar products. This is 1D, and this is also 1D. You can put them together as a 2D scalar product. And this gives rise to this family here, phi 1 and m, tensor phi 2 and m. And one can show that this family is almost orthogonal, which clearly proves that this operator should map L2 cross L2 into L2. And this family is almost orthogonal as long as the two caps that are defined by U1 and U2 are disjoint. So this is how we exploit transversality in the bilinear setting. We take these joint caps. This guarantees that this family is almost orthogonal, and then by Plancherel, BE maps L2 cross L2 to L2. That's the idea, and then we bootstrap that in higher dimensions. In a sense, it's not as simple as I'm making it sound, but that's the idea. And the second building block is Thomas Stein or Strickhertz. The idea is that we can combine these two tools at a local level, and this allows us to finish the proof of the K-linear theorem. Roughly speaking, we can take advantage of a local factorization, and I put quotes here because it's not the true factorization; it's a moral one, but we can take effective advantage of that at a local level. In the K-linear problem, we can factorize it into several 1D bilinear problems and a Thomas Stein, if you assume only weak transversality between the caps. Okay, I'd like to finish with some final remarks here. That when K is D plus 1, so in the BCT case, we actually recover the endpoint. Our proof doesn't go just up to the endpoint. We actually recover P equals 2 over D. And if you assume more transversality conditions, and I'm going to keep that vague because I'm running out of time, you can improve the conjectured range in the K-linear conjecture, assuming that one of the functions has a tensor structure. And this is only in the case K is not equal to D plus 1. Also, we give the same treatment for both linear and multilinear problems. So the proofs of the theorems that we can get are all in the same framework. And this holds for both linear and multilinear at all levels of multilinearity. So the K-linear theorem, in a way, is as hard as the bilinear theorem. The tools are the same. All right, and that's all I wanted to say. Thank you very much. Thank you for the invitation to speak at the seminar.